Today we are going to talk about things that move in a circle. We have discussed objects that follow curved or parabolic paths, such as our projectiles when they had both vertical and horizontal motion. But whenever it came time to analyze the motion or perform any calculations, we always kept our calculation so that it was along the horizontal axis or along the vertical axis, where we were still dealing with just one dimension or linear motion for each of our calculations. We have not actually done any type of math work where we are analyzing the curved part of the motion. And so what we are going to do today is begin analyzing objects that are moving along a curve. And in this case, most of our objects are going to complete that curve all the way around until it makes a circle. And so now we are going to begin talking about both curved motion as well as continuing to discuss the linear motion that we've talked about in the past. So linear properties, or linear meaning along a straight line, these are going to be things like our linear velocity that we've talked about before, acceleration, displacement, and force. These are all variables that we've discussed in the past that are linear variables, and we are actually going to continue using these terms throughout this chapter as well. But now we are going to introduce something that is called angular. And anything that is angular, is going to be along a curved path. So angular means curved. And we are going to learn some new vocabulary today that is going to have the word angular attached, which just means it is a measurable variable, but it's going to be along the curved route now instead of being represented with a straight line, okay? So let's get some basic vocabulary. First, when we talk about circular motion, we often hear our objects are being described as performing uniform circular motion. And whenever we say uniform circular motion, we mean constant or steady. So uniform circular motion means that our object is experiencing a constant speed as it goes around that circular pattern. Okay, so uniform circular motion is constant speed as it travels around the circle. The center of our circle is going to be called the axis of rotation. Now, why we can't just refer to it as the center of the circle and be done with it, I'm sorry, I don't really have a specific good explanation for you there. This is just the proper terminology. So if we are talking about a circle, the very, very center is going to be referred to as the axis of rotation. All right, so then next we have two vocabulary words which are used to define, explain, describe, identify what type of circle our object is making. There are two choices. We could have objects that you and I say are spinning. So for objects that are spinning, you and I would say that an object spins. We would say that this ice skater here is spinning or twirling. But in this class, I need you to reprogram your brain. Spinning is now going to have the term rotation, okay? So when we say rotation, this means that the axis of rotation, aka the center of the circle, is located inside of the object. So if we were to stand up and spin, the circle that we make would have the center located right between our feet for excuse me, walking, so that we make that spin. If we think of a point from above, it would be right in the middle of our head, pointing down, that would represent the center of the circle. So whenever that axis of rotation or that center of the circle is located inside of the object, so the center of the spinning skater is inside of her own body, we are going to call that rotation. Now we also have what we call a revolution. Now this is something that you probably are more familiar with than you realize. We know that the earth revolves around the sun. And so that means that the earth is going to orbit or move in a circular pattern so that the sun ends up being the center of its circle. So the object that is going around in a circle is the earth. But the center of that circular pattern that it is following is not located within the earth itself. It is located outside of the earth. In fact, it is located at the sun. So when we say a revolution, this is where the axis of rotation or the center of the circle is located outside of the object. So these are some basic vocabulary words that you will need to know and be, excuse me, be able to correctly identify these definitions in the future. All right, this is just an overview. My second circle here on the right transferred a little funny. We're going to pretend that is a nice, pretty circle, not an oval. But I just want you to see, moving forward, we are going to continue to talk about force, acceleration, velocity, and the radius. These are all linear straight line properties, but we are also adding some new things. This second picture has some new symbols for us, and that's the new vocabulary that we are going to learn today. So the first thing that I want you to focus on is this very first bullet here. The word angular means curved. That's a really important statement. And so I want to make sure that you get this in your notes. The word angular is going to mean curved, okay? Which for many of our situations would also be described as the motion around the circle. So as we continue through the notes today, you're going to get a few different words that are going to be angular something. Anything angular, we are now talking curved, okay? So now we are dealing with motion that is along this type of path. It is going to be a curved path. So the first thing that we have here is angular velocity. Now you already know that velocity is displacement over time. So let's look at how the definition changes because we say that it is angular. We have learned V equals D over T as our formula for velocity, linear velocity, straight line velocity, where this is a displacement, which is going to be a change in position or how far along a straight line, measured in meters over time. And time is scalar, it has no direction, right? And that's going to be measured in seconds. So we have already talked about linear velocity, where it's a straight line, how far. We would use a meter stick in order to give us that numerator value. And so this would give us something measured in meters per second. When we see the word angular, now we need to think about this is no longer going to be a straight line, that this is now going to be a curved path. So this numerator of displacement would now more accurately be described as angular displacement. So now this is going to be a how far around some curved pathway. Angular displacement, curved displacement. It's still going to be over time. And so this is velocity, but it is curved velocity. So what you see here on the slide is that it says angular velocity is the rate of angular position change. Change in position is just the definition of displacement. Angular just means curved. It says here that we are going to use the Greek symbol omega to represent our angular velocity. So this is going to be our omega, and this is going to stand for angular velocity. Think of it as straight lines make the letter V for our straight lined linear velocity. So V equals d over t. That's a straight line V. So that's straight line linear velocity. We have curves here that make up our symbol omega. So our curved velocity is going to have the curvy symbol, okay? I know that's a little corny, but hopefully that will help you understand. Now, when we talk about displacement around the curve, we have spoken in the past about curve displacement. If you think back to our introduction to projectiles at an angle, we were looking at a circle and we said this right here would be 0 degrees. This is 45 degrees. If we go perfectly straight up, that would be 90 degrees. And so all of these were basically ways of saying how much of the curve we have covered. So this angle that we've already covered is now going to be our angular displacement. If you take your hand or your arm and you start perfectly horizontally, and then you raise your arm to 45 degrees, raise your arm to 90 degrees. Now, imagine if your fingers were drawing a line in the air. You would end up making a curved line, okay? So when we talk about this displacement around the circle, we are talking about our angle. And our angle is going to be represented with the symbol theta. So angular displacement is going to be theta in the future, okay? Now, when we'll get to that full formula in a moment. When we look at this image right here, I want you to focus on the angles in degrees that you see inside. So if this would be the 0 marker, this is 45 degrees, this is 90 degrees, okay? We can keep going around 135, 180. And so when we look at these angle values, they are simply telling me how much of the circle I have covered. I have covered 45 degrees. I have covered 90 degrees. Do you see now that I'm tracing it? Yes, by following that degree marker, I am basically tracing a portion of the circle. So if I tell you that we start at 45 degrees and we rotate to 90 degrees, well, this is my curved or angular displacement, right? So theta is now going to tell me what that displacement is. Now, in the previous chapters, theta or our angle was measured in degrees. Again, why can we not leave it in degrees? Well, honestly, it comes down to the way that the formulas were written. They were not written to show relationships for angle measurements in degrees. Instead, they were written to show relationships for angle measurements in radians. So if you look at this image, everything in red represents radians. Now, perhaps you have already been exposed to this in your math class and you are already familiar with radians. If you are not, don't stress out over it. I just want you to get it in your notes. I want you to get it in your mind that our angular displacement is our angle. That is the symbol theta, which we have seen before, and it is now going to be measured in a unit called radians, okay? So let's go back to our conversation on the previous slide. Our angular displacement is going to be measured in a unit called radians, which we will often just abbreviate rad. Theta is going to be our symbol for the angular displacement. Time is still going to be the lowercase t, and we still want time to be measured in seconds. So when we look at this fraction, rather than getting meters per second, because we're measuring our angular displacement in radians, we are going to get radians per second. So let me zoom out here, and I'm going to kind of move this a little bit so we can clean up our slide. If we talk about the symbol for angular velocity is now going to be this symbol omega, and we are going to pronounce it omega. You might think of it as a W, but W will represent a different variable in the future, so please train yourself to call it omega. This stands for angular velocity, and it is measured in a unit called radians per second. It is measured in radians per second. All right, so what we are learning on this slide is our first new formula for circles. This says omega is equal to theta over t. What this means is what I just spelled out on the previous slide. Our angular velocity is now going to be calculated by taking our angular displacement and dividing that by time. Our angular displacement is going to be in radians. Our time is going to be in seconds. So we are now going to end up with the unit of radians per second. This would be in radians, which we often just say rad for short, and time is going to be in seconds. Okay, so these are the new variables. Just how we would identify displacement as being positive or negative depending upon the direction when we are dealing with linear motion, we are still going to have positive and negative directions for our angular displacement. So you can see here clockwise, which would be this way around a clock, is going to have a negative displacement, and counterclockwise, which would be this way around the clock, is going to have a positive value for its displacement. All right, so what about that linear velocity? That linear velocity is still part of the conversation. Now you can see here that it says linear, and then in parentheses it says tangential velocity. So let's talk about that for a moment. Hopefully in math class you have learned that you can have a circle where there is a line that touches or intersects that circle at only one place. Now that line could be anywhere on your circle. It's just only allowed to touch the circle at one point or at one location. So there is a math vocabulary word for this line, and it is called a tangent line. So the tangent line represents the line that touches our circle in only one location. So it's got to be on the edge of the circle. You can't draw it through the middle of the circle. This tangent line is also going to represent our linear velocity. If you recall, we spoke about a car that was traveling at a constant speed of 30 meters per second while driving around a circle. And at the time, our conversation was yes or no, is the velocity constant? And we decided that the answer was no, because if the car is driving counterclockwise at this moment, that's the direction of the car. But then as the car turns at this moment, this is the direction of the velocity of the car. And now at this moment, here is the direction of the velocity of the car. And so we spoke at that time, and we said that the velocity was not constant because we were discussing linear straight line velocity. And you can see from these straight line vectors that the direction is changing. What direction I point that arrow in changes. Well, we are going to take that conversation and we are going to add it to what we are learning about our circles. If we have an object that is moving in a circle, its path of inertia is going to also coincide with that linear velocity, or it's going to be represented with a tangent line to our circle. Okay, so the word linear velocity means the same thing that it meant to us in previous chapters. Linear meaning a straight line. Tangential, with the root being tangent, and I've already explained what a tangent line is. So don't get confused in future questions. You may see it written as linear velocity. You may see it written as tangent velocity. Or you may see it written as tangential velocity, but they all mean the same thing. They mean that we are talking about straight line velocity, which we represent in our class with the letter V. This is still V equals D over T. Okay? Nothing has changed. This is still going to be in meters. That's still going to be in seconds. So we are going to end up with a unit of meters per second for our linear velocity. Okay, so how does this relate to our circles? If I have an object, imagine that you are twirling your lanyard. You're not wearing it on your neck like you're supposed to, and instead you've got it in your hand and you're spinning it around. If that lanyard slips out of your hand, if you accidentally let go, what is going to happen to that ID and that lanyard or the ID attached to the lanyard? What happens is that it flies off of your hand. How does it fly away? It flies off, at least initially, in a straight line. What direction is it going to fly off? Whatever direction it is moving at the moment that you lose your grip. Okay? So if you let go while your lanyard is moving towards the ceiling, then your ID is going to fly straight up in the air. If you let go while your ID is moving to the right, then your ID is going to go flying off to the right. And so what we need to now understand is that linear velocity, or that tangent line velocity, represents the direction that the ball will go if it exits the circle or leaves the circle. It might be easier for you to think of the tangent velocity as the path of inertia. Now, we are not going to watch the video at this moment, but I often show a video of some kids on a merry-go-round. They use a motorcycle type of bike, excuse me, a motorbike of some sort, to cause the merry-go-round to spin really quickly, and a kid gets thrown off of it, and he flies off in a perfectly straight line. That is the linear velocity, or the tangent velocity. We initially watched that video talking about inertia, and I said, look, the path that he is following is his path of inertia. Well, now I would use that same video to say the path that he is following is now going to be identified as his tangent velocity. We have a couple of more equations for you here. The first one is V equals omega r. So this is saying that my linear velocity, measured in meters per second, is equal to the angular velocity, which is measured in radians per second, times the radius of a circle. And this is going to be measured in meters. So let's not forget our basic geometry. If I have a circle, here is the center of the circle, aka the axis of rotation. If I measure from the center of the circle to the edge, that would represent my radius. It's a how far measured in meters, okay? So what this is telling me is that there is a direct relationship between the tangent velocity and how fast I am spinning, that object. So if I have my ID on my lanyard and I'm twirling it around, if I twirl my lanyard super fast, then if I lose control and that ID goes flying out of my hand, it's going to fly out of my hand really fast. They're directly related. If I maintain the speed at which it is twirling around, but I change the length of my lanyard, so maybe I'm holding on with half of the lanyard that's able to twirl in the circle, and then I decide that I want to just go ahead and let that lanyard slide all the way to the edge. So now the whole length of the lanyard is going around in the circle. This is saying that there is a direct relationship between that tangent velocity and that radius. If I were to twirl my lanyard so that it makes a larger circle, if I have a bigger radius, that is going to result in a greater tangent velocity if it goes flying out of my hand. Our second equation here says V is equal to 2 pi r over t. Now again, these are both ways that we can calculate tangent velocity. So yes, we could say V equals d over t, but because my object is moving in a circle, we are most often going to get information around the curve of that circle to allow us to figure out how fast my object is moving on that straight line path. So what we have here is we still have a how far over t. We have 2 pi r measured in meters, and we have a t measured in seconds. So this still gives us meters per second. Now, I just want to take a moment and break down the meaning of this equation for you. So this is not something that you're going to have to recreate for me in the future, but I want you to understand how these two equations are both acceptable ways to calculate that linear velocity. They're basically giving me the same calculation, but the set of variables that I have to work with is different. So when we're working through our word problems, we really want to make sure that we are listing our givens in detail, symbol for the variable, the number, and then the unit that goes with the number, because we've got lots of variables that are new to us in this lesson, and then we've got some variables that are just going to be confusing because we have linear and we have angular. Is it this? Is it that? We've got some new symbols to go with the new vocabulary, and it's just a lot of things that are new. It's going to be really easy to get things mixed up, so make sure you do your givens in the complete form according to how I taught you to list your givens. So when we talk about 2 pi r, 2 pi means that we have done one full trip around the circle, okay? 2 pi just means one complete circle. So if I say that I have 2 pi, I have basically said here is my theta. 2 pi represents theta. If I isolate my 2 pi over t, well, we've already said that 2 pi can be replaced with the symbol theta. Well, what is theta over t? That was our very first new equation for today. Theta over t represents our omega. So this theta over t can now be replaced with the symbol omega. So if I have 2 pi over t, all of this can now be replaced with omega. And then the equation says, so I've accounted for all of that, then the equation says times r. And that takes us back to our original formula from this slide. V is equal to omega r. So what I want you to know is that these two equations are both acceptable equations for how we could calculate the linear velocity. It is just going to depend on what set of variables we are given as to which is the appropriate one for that particular situation. All right, now I'm going to skip down to a little summary of some of our new variables. So I created this slide just so that you can have an easy reference. Omega is a new word for us. Most of us are not familiar with the Greek letter omega, so just the word omega all by itself is new. Omega represents a new variable for us. This is angular velocity. And angular velocity is measured in new units. We have radians per second. Then we have our Greek letter theta, which we've actually seen before, but it is still fairly new and a lot of students are still learning what theta is. So theta represents the angle. And as we have reviewed, the angle basically tells me how much of the curved path we have traveled. So we are going to say that theta represents our angular displacement. It is measured in a new unit called radians, which we often see abbreviated as just rad. So this is just a little summary sheet that will hopefully be helpful for you and allow you to get more comfortable with some of the new variables and new vocabulary. This kind of summarizes the difference between angular and linear velocity. So angular means curved. Linear means along a straight line. So we are going to have our linear velocity, which is our straight line velocity. And so it says here that all points on the object do not have the same tangent or linear velocity. If I remember that the linear velocity is dependent upon the distance from the center of the circle, aka the radius, objects that are traveling in a small circle will have some velocity. But if I take that object, keep it spinning at the same rate, but I simply increase the size of the circle or increase the radius that it is traveling, well, that is going to increase that linear velocity. So there is a direct relationship between linear velocity and radius. The larger the radius, the faster or the greater that tangent velocity. So it is going to be different depending on where the object is located on our circle. Then it says that our angular velocity, so the omega angular velocity, is going to be the same everywhere. As long as this entire thing is spinning at the same speed, then it doesn't matter where we are on the circle, that rotation is the same for the whole piece. So this entire circle is going to rotate together. I will not rotate this part of the circle without rotating this part of the circle. They both rotate together. So that's what we mean when we say that our angular velocity is the same everywhere. It doesn't matter if we're close to the middle or if we're close to the edge, that angular velocity is going to be the same no matter what.